Okay, so here we have three molecules. We're going to do the resonance structure and assess the structures to determine which one contributes more to the resonance hybrid. So the first molecule here, this is phenolate anion, and that is the conjugate base of phenol. This is phenol. So after you remove that H, you get, this is the conjugate base, phenolate. And we are going to draw all of the lone pairs. Oxygen with a negative charge will have 3 lone pairs, so there's 3 electrons. I'm going to do the same for the other atoms here. Nitrogen, remember this in ammonia, nitrogen with a negative, with a 0 formal charge will have 3 bonds and 1 lone pair. So that's the case here. 1, 2, 3 bonds, 1 lone pair. Here, this compound is aniline, and this one here at the bottom is pyridine. Here, nitrogen has 1, 2, 3 bonds, so I need a lone pair. All right, so let's do the structures now. Phenolate, notice that these two positions are vinylic. So one of these lone pair is going to be delocalized, not. So we can, in other words, do resonance. So, but if I do that and make a double bond here, I must do another arrow because I don't want to break the octet rule. So what is the structure that results from that movement? Is the following. I'm going to put electrons here so that we keep track of that. So 2 lone pairs now and now. But again, we have the pattern is repeating. So we have the 2 vinylic position and electrons at the allylic position. So I can move those, right? So I can do resonance and put the charge right here. Again, most do 2 arrows because you don't want to break the octet rule. All right. Let's do that. I'm creating a double bond here, see? And because I'm moving that, lone pair is here and double bond here. All right. Let's see, can we keep moving electrons? We can. Lone pair here is allylic to this double bond, so I can move it over to the other side. Of course, I could do that, but so the other side, but I'll get back here, and that's not what I want. See now, I need to localize the electrons at that carbon. So the next structure is going to be double bond here. Then I have that, and I'll have a lone pair here. So in regards to now the hybrid, let's see how this structure contributes. In all of the structure, octet is complete everywhere. So we have 8 electrons surrounding the oxygen and 8 in each of the carbon. Remember that this is true because you have H's all over here. So if you count the bonds for each of the carbons, you have, say we grab this one, 2, 3, 4 bonds. So octet is complete in all of the structure. That is the same for all of these. But what is different is that in this structure, this 3, the negative charge is on a carbon. And here, the negative charge is on the oxygen. So that's the structure that contributes the most to the hybrid. So if I can draw the hybrid the following way. So I will do barely that. And yes, electrons are going to be delocalized. I'm going to have partial, double bonds. But at the oxygen, I'm going to put a larger delta negative than I do here. Notice that the negative charges are here, this position, then the other position on the other side, and at the end. So, but because this structure is the one that contributes the most, I'm going to have the larger say, partial negative charge. All right, let's do the next structure, which is aniline. So here, oh, I forgot to say, remind you that this oxygen then is sp2 hybridized. So when it is at that allelic position, so you will have that lone pair, that you can have that orbital overlap, let's say. So you can move those electrons, in other words. Here, the nitrogen is also, we're going to say, is sp2 hybridized, so that the lone pair here at the nitrogen, say we will have sp p orbitals all over here. All of that is sp2 p orbitals. They can do that overlap. If you say that this is sp2, you can also have that overlap. So next to each parallel like that. So I'm going to move those electrons, meaning electrons at an allelic position. These are the two vinylic. This is allelic. So I can move those. So I will delocalize those electrons and make a double bond here. I needed necessarily do this movement, and in doing so, I'll be making the following resonance structure. Double bond here, NH2. Notice that now nitrogen has 4 bonds, 1, 2, 3, and 4. So that's a plus formal 1 charge. And now I'm gonna have the lone pair here, so that's negative formal charge. And still I see the pattern where I have an allelic lone pair. So I can do this movement. And in doing so, we are creating the following resonance structures. So here, NH2 plus, I'm going to be making a double bond here, and now lone pair is in this position. I can still moving that because these are at an allelic position again, and I can do this. In the structure that results is, say, the following. Now I'm going to have the lone pair here. And this is NH2, same formal positive, that and that is structure. And, oh, it goes. Disappearing bond. Let's see if I have a, I cannot let that happen. Oh my God. Okay. I'm going to do another color because it's barely visible. Okay, I hope that's better now. Okay, you guys. Now from this structure, I can see these two are the vinylic positions, so I can move lone pair over here and now move it over to the nitrogen. When I do that, this is a structure that I create now. I'm gonna have NH2. I did that movement, so I'm gonna have my lone pair back here. Double bond, double bond, double bond. So notice the initial structure in the final. These are Kekulé structures. What I did is like moving the bonds, the pi bonds in the, say, benzene ring. So these two structures contribute the most. So say they are Kekulé structures, just if you see the bonds in the ring. And I don't have formal charges. Octet is complete everywhere. So these two structures contribute more to the hybrid. And contribute equally, the same. This do not contribute much. You're creating charges. Octet is complete, but you're creating charges. So definitely the hybrid would look more like this too. So I'm going to draw a hybrid structure here. And I'm going to have the nitrogen acid. So I'm going to make these two, say A and B, the most contributing structure, and draw the hybrid. Since here I have single bond and here I have a double, so I'm going to do partial. And same everywhere. So here I have a double, but here's single. So if you can see, we have partial double bonds everywhere. So in many cases, you may see this even in books. This only signifies that these electrons are delocalized, and all of the bonds in the ring are equally in terms of distance and strength. Okay, so these are the most contributing structures. So finally, I have here the structure of pyridine. What's different here? The difference is, yes, the Nitrogen is sp2 hybridized as all the carbon atoms, but I'm going to make a different drawing of that, which is the Harvard projection for that. And here, let's say that I put my nitrogen here. Anywhere is the same, but if, for the sake of the explanation, that is a plane perpendicular to the board. And since everything is sp2 hybridized, I'm going to put just the orbitals. Now, sp2 hybridized means you have a p orbital like that. And all of those electrons are delocalized all over here in the ring because you have all of these overlap. However, here you have a lone pair. The lone pair here is actually localized because it is localized because it is at a binary position actually. There are in the sp2 orbital, in that orbital is perpendicular to the p orbitals in each of the bonds. So again, you cannot, we say these are localized, cannot move those. So the only resonance structure that can generate is, say, the corresponding calculi structures. See the arrows that I have, nothing else, because the lone pair here is localized. So important to establish the difference. Here, the lone pair in aniline is delocalized. You can move those. They were at an allelic position, and we were able to do all that. Here, lone pair in the phenolate is also, one lone pair is delocalized. You can move it. And pay attention to the difference again. If you see that the double bond is between with the nitrogen, so they are at a binary position, then the lone pair is perpendicular to the pi cloud and therefore is localized. You cannot do resonance there.